is another Verilog video of a real interview question. And I'm going to go through what this interview question is. But this interview question, there was only like 35 minutes to do it because they were like late. And then it took them like 10 minutes or 15 minutes just to log into CoderPad because CoderPad is a crappy platform. It doesn't even have synopsis, so you can't actually even write Verilog. And well, I mean, I'll let you be the judge of it. But basically, for this particular company, which I won't name, like only 2 of the 5 interviewers were actually good at defining the problem, and this wasn't one of them. Like I asked a few clarification questions, but a lot of times the response is just silence. And I'll show you what sorts of clarification questions I asked so you can kind of be the judge of yourself. If these are actually bad interviewers or if I am sour grapes and just trying to thrash people that didn't pass me in their interview. So by the way, I failed this one. But I will say of the 2 out of 5 that were quite well defined, and even if I struggled a bit and they didn't pass me, I would say those I failed sort of fair and square. But this one, yeah, I mean, like if as an interviewer you're not answering qualifying questions, it's kind of hard to solve the problem because you don't know what problem to solve, basically. So I would say, yeah, I mean, I guess, like, long story short, this company would have paid a lot of money if I got in, but I didn't get in. But even if I got in, then there's always the worry of like, well, do I really want to work with people like that where like they can't even define a problem? Like if they assign you task, but they don't even tell you what the task is, for example. So their description of the problem, which I will go through now, is basically, and this is a lot bigger than most Verilog problems that you'll see. Write an M to N mux whereby you have M streams going in and N streams going out, and you have packets that you want to output. The output stream must have the same packets, and the incoming packets will increase monotonically. And then the packets incoming, you can assume, will start at 0. I tried to make this as confusing as run-on as possible, but it's probably still less confusing than their crappy description. And they said, yeah, like we'll go silent for a few minutes, let you read it. But as soon as they pasted the problem, they like kept talking at me, so I couldn't even read it. So it's quite annoying, but I will do a much better job of explaining it than they can, because I'm pretty sure no one on earth could do a worse job than these retarded interviewers. Basically, you have M streams going in, and you'll notice on the left-hand side, they didn't even provide parameters for M and N, so that's not even correct. Okay, so you have M on the left-hand side, and then you have N streams going out. In this case, 4 and 2, but you could say like 4 and 3. Well, whatever, right? And then, so basically what you want to do is for each of these lines, data is coming in each of these lines. And each piece of data has a packet number, which they called sequence instead of like packet number, which, that would make way too much sense. And then so the sequence, which is the packet number, all of these lines, when they send valid data from reset, it starts at 0. So for example, the first piece of data might have like data equals, dead beef or whatever. And then, value would be 1, and then sequence must be 0. And then only yeah, so all of these lines, if they're valid, they start at 0. And here's a clarifying question I asked, because I'm like, okay, well, this is data in, this is valid and ready in. And I asked them like, okay, well, why do we have a valid here and why do we have a valid here? It seems like, this valid is sufficient, or this valid is sufficient to qualify the data. And they just said this valid ready qualifies the rest of the inputs, which doesn't make sense, right? It's not first, it's not the rest of the inputs, it's just these sets of inputs. And these qualifies the rest of the inputs, but then that doesn't answer the question of like, why do we also have a valid here? Like it seems redundant if you have that. I also asked if, let's say, so when you have a startup packet, the definition is, if I have a startup packet, then I'm going to start sending sequence of like, let's say 0 in, and then when I have like end of packet with valid ready in, then that cycle will be the last of the current number. So for example, if valid in and ready in are both 1 equals 1, and then current, like the sequence of the data is 0, then we're guaranteed not to have, and then also, let's say for like line number 2, so where m equals 2. So if we have, valid in and ready in is 1, and then sequence is 0, and then let's say we have end of packet in equals 1, then we're guaranteed not to have any data struct with valid until the next start of packet in. And once we encounter this, this will increase monotonically, meaning all the data packets coming in will have sequence 1 until you have end of packet in, with the handshakes, of course, and you have sequence 2 and so on. And then the objective is to produce these outputs whereby you're passing these data in to data out, and then your valid out will be corresponding to end lines, and then your output packets also must adhere to this sequence rule, meaning it must be also monotonically increasing. So what you want to do is you basically want to scan all the inputs, which all start at 0, and then exhaust all the lines zeros first before you assert this end of packet on the output side. So that's that. And yeah, they didn't really answer like a lot of questions. And then when I asked, I think I asked also about like, I asked about like this valid because that was really confusing. Didn't really get a good response. And then I think I asked like if in between start and end of packets, what happens if, these are valid. They didn't really respond. So I just said, hey, like maybe I can just assume there's no valid. I think these handshakes are somewhat important to clarify as an interviewer, because that's kind of like you need to know the handshake to implement it, right? Anyway, they asked me like if I knew AXI interface or some other interface. I said I knew AXI, and then they're like, well, this is the other interface, but then they didn't really define it. So it's like, I feel like a lot of these, you just kind of have to memorize a lot of these problems and practice these streaming mux in, mux out problems over and over again. So then you can just internalize what is the most likely thing that they're asking about. And even as I will try to solve this problem, I still don't know if these are the specifications that they wanted. And then after I solved this one, the next problem, like they asked me something I didn't know, like some syntax I didn't know in Python. I'm like, I don't know this, so I will try to implement it. So they tried to define it but they defined it much worse than like the Python documents, because the Python documents, you read one paragraph and you'll understand it, but the way they explained it was like pretty bad. They could have just copy pasted the Python document, to be honest, and I would have understood a lot better. But anyway, the initial understanding was actually correct that I had, and then I wrote the correct implementation, but then they really hinted for me to want to return a function pointer as opposed to a value. So they really urged me to do that. So I'm like, okay, cool, I'll do that. And then once I did that, they're like, no, yeah, like this is wrong because you need to return the value. So it's like, yeah. I feel like the interviews went a lot better if like they didn't open their mouths and actually just let me work on the problem. But I feel like a lot of these are like just to throw you off, maybe. I don't know. Also, when I was interviewing with these folks, like they seemed quite unhappy. Like they're like me when I'm like frustrated with like a coding problem, with like a side project or something. But they're like that all the time. So yeah, I mean, except for like the 2 out of the 5 folks I talked to, like the 2 people that, I don't know if it's correlated, they defined the problems really well, but then also they didn't seem like they have a stick up their butt. But anyway, let's try to solve this problem. So the strategy, will be greedy. You could also have like a buffer that will kind of like do a wide round robin. But in this example, what I will try to do is just a simple case. Let's say it's like 7, and then it doesn't really matter, but this is just for correctness. Let's do prime numbers because prime numbers are cool. So suppose you have 7 input streams. They all start at 0. So what you want to do is you want to just suppose you have like I will denote like m of 1 to 0 valids like this. This will mean stream 0 is valid, stream the third and fourth stream is valid, last stream is valid, for example. So for example, you have this, then you want to pack it into, let's say, this, and then you want to back pressure this last thing, and then suppose now the next cycle is like this, then I'll just be greedy. I'll just pick the first 3. It kind of doesn't matter which ones I pick because the throughput will be 3 anyway. In that sense, if my output's 3, and then let's say like, these have nothing, and then there's only 1, for example. So in this case, I still back pressure this last one, but there's no real deadlock situation because suppose I exhaust all the other streams. If I exhaust all the other streams, then the last stream will be at like I will only not back pressure the last stream, which is still 0. Now the most optimal would be like if I did these 3 on the first cycle and I put it out into the output streams like so, then I'll back pressure these, but then the next cycle I'll round robin and start here, or I'll start here. And then this is similar to the previous packing problem where you would pack this and then you would back pressure the ones that you didn't grant. And you would just basically keep a counter of like how many that you packed out. So if you packed out 3, for example, you might have another counter as you pack to know that like, hey, this was your last index, so start here. And then your counter would just basically be a round counter where you start here, but then if you have like equals, for example, n input streams, your next count will be just back at 0. And then that's how you would do your packing. That's a little bit more complicated because you need to keep state. So in my case, I will just always do like a priority encoder and go for the first 3, and then the last streams, unfortunately, it will be like a longer latency if they all have like, for example, uniformly the same amount of packets. I'll leave the extension as homework to the reader, but with 35 minutes, it's like really hard to implement a lot. or if there's like a surprise, if I if I implement this in a very short amount of time, I'll do the extension, but I doubt that. Okay, so first, we can maybe start backwards, and well, first we need a structure that says packet number for input stream and then I will also just say, like, just rewrite out the spec. Packet numbers sec for M streams always, like, at reset starts at 0. Packet numbers are terminated for a given input stream when valid in and ready in and end of packet in. Once packet numbers are terminated, the next set of packets that'll be indicated by valid in and ready in and start of packet in must have its packet number or sequence be 1 higher than the previous packet number. So 0 to 1 to 2 to 3. Okay, so let's maybe implement this. So if valid in and let's just do for stream. Also, they wanted me to not do this first, and they really wanted me to do this packing first, which is kind of annoying because it seems like micromanagement. If you hire an engineer, you want them to just solve the problem in their own way and just get the result, as opposed to kind of like interrupt them. So I feel like as an interviewer myself, I like giving candidates the latitude to approach the problem however they like. I might give like high level stuff as like, hey, maybe we spend a few minutes just defining like high level what your solution would be. We can kind of talk about it, and maybe once we both agree, then we can go ahead and implement it. Whereas here, it's like, I want you to implement this very specific part first, but logically speaking, it might not make sense to do that first, given the person. So this is just trying to satisfy if I have like the end of packet, then the next time, we have a startup packet, then we must guarantee that it's the current packet number will be like 1. So, and we're guaranteed also that end of packet won't arrive before startup packet, but they said end of packet and startup packet could arrive in the same cycle. Here, I don't care if end of packet or startup packet arrives in the same cycle. Because I'll increment it 1 more for like the next, like this variable says I want to anticipate this specific packet number given each input stream, and then this is going to be used as a cam So I'm gonna run the cam across all inputs to see if, like the current state of the output, which is, let's say, packet number 0, matches. So if a particular input streams at packet number 3 and then the output streams at packet number 2, then it will just ignore that input stream and then just back pressure it, if that makes sense. So then this just handles the monotonically increasing case. I guess I don't really get the start of packet thing because the assumption is that the starter packet might indicate like the next thing, but then they also said they won't have any. Well, I also made the assumptions that they won't have any valids if there's no starter packet in. So it's really the end of packet that signifies the next. So I guess this is don't care. So I hope this makes sense. This is just the current state in terms of packet number with respect to each input stream, of which there are n input streams. And then the other thing I need to handle is like, what is my current state? So my current output state, or the current output packet, the current output packet is going to be the minimum of the packet. Like, for example, if this is like 0, 1, 2, 0, 0, 0, like it'll just be the minimum. So I'm wondering if there's a more elegant way to like just scan the minimum each time, like. Oh, I see. So what I can do is to say, this also starts at 0. And so this is already a lot more relaxing than the interview because like I'm not being interrupted every 5 seconds. Always. So what I can do is I can say for int I is 0, I is less than all the input streams, I would like to compare the output packet number to see if it equals to each of the streams current number. So if any of it is equal, then our output packet number shouldn't update. But if like we all start at 0, then there must be a state where there are no more zeros, and if there's no more zeros, there must exist some ones. So then we can just increment by 1 because they're all monotonically increasing. In fact, they must be all 1s. But I can just simplify it by saying, hey, every check cycle I'll scan across the input vectors, and if there's no more zeros, that must mean the output packet number can now increase by 1. Hope that makes sense. If then I want to break basically, and I can start at like I can just do something like this, like increment output packet number is false to begin with, and sorry, it's true to begin with, and then if I scan across the entire thing and it's equal, then I'll set this to false. And then actually, this is just going to be like that. So if we scan all the input streams and none of it is 0 anymore, then we go ahead and increase this because this will never hit, and then the default value will trigger, so then we'll actually increase it. And then since they must be monotonically increasing, then the next thing, they should be all 1s in the input stream. And then basically the next cycle, we would always have something that would hit until all of these go to 2. And then the out packet would increase accordingly. So that's that part. And then another part is the actual, maybe I can zoom in a bit for the blind viewers. So the next part is actually outputting these guys. So this can be quite combinational. One thing to consider is this cycle or next cycle. So the out packet num is going to be increment, like if everything goes to 1, then or rather, suppose a case where you have the last of like packet number 0, then you hit this case, and then only the next cycle will just go to 1. When this next cycle goes to 1, then this will go to 1 in the next cycle. So after a last packet, 2 cycles later, will you actually propagate this thing? So we could maybe resolve that bubble by doing, we actually might want to go back to this, because I think also in the problem it says minimize the latency. So instead of checking against, when I cam against all the inputs, instead of checking against this number, which will take, 2 cycles, the 0th cycle being the last valid data coming in for, let's say, packet 0, and then the first cycle being a bubble. Second cycle is kind of when you'll start outputting again. We can cut a cycle off that, so it's more back to back, like valid of the last one, and then you have a start of the next one. Then you go ahead and output it. So we can check against this when we cam, as opposed to the other, as opposed to this, and that'll cut out a cycle. but then it would be the critical path of this. That might be okay. There's no infinite loop of combinational logic that I'm concerned, because this is right out of a D flop, and ergo this is also right out of a D flop, and then this is also right out of a D flop. So sorry, Q pin of a flip flop. Okay, so this part is I kind of just want to see like how to do the data out, for example. And this is kind of like boilerplate packing template that we've worked on a few times now. And then you might have like basically logic of which is J, and then you can have like J equals 0, and then you can do like for int of if let me move this up so I can see the actual interface here. If data in dot valid, so the data packet must be valid, obviously, and actually I'm scanning the input. J is counter index for output and output. So this data stream for I of M is valid, and valid in of I, and ready in of I. They said these two qualify the rest of the inputs, which could mean like just, yeah, I mean, okay, yeah. So I guess this like is like double insurance, like you get this handshake on input I, and then also the valid of the data on input I, and data input of I's sequence is going to be equal to this next thing, which is also 9-0. So to reiterate, this is a handshake to make sure that an input for stream I is like qualified properly, and then also we need to make sure that the input I's packet number is actually what our current state is. And even if we have n packet for this particular cycle, then that's inclusive, like we need an n packet even if your sequence or packet number is 0. So even if this was asserted at this exact cycle and this is asserted next cycle, then the data in this particular cycle should still be packet number 0, for example. Not sure if that makes any sense. And then so if this is good, then this is actually something that's valid, and J equals J plus 1, meaning we've packed it for 0 and we need to move it to the next. And then the data out of J, which in this case before this update would start at 0, but then it will increment to 1. This would then be data out J is basically data in of I, and then also valid out of J is going to be data in of I. And then whenever you're adding these variables in the loops, you kind of have to be very anal about it. Assigned to 0, otherwise they're like, oh, you're implying a latch. Which is annoying, because obviously, like, if you know anything about Verilog, like, it's obviously just a typo as opposed to a fundamental misunderstanding of how things work. So anyway, you reset these as data and valid out as default to 0, and then you basically pack the inputs to the outputs, where you scan all the inputs to be qualified properly, and then if and only if it's actually properly qualified do you increment the output index. Okay. Now, this problem is only interesting when m is bigger than n, because obviously if m is less than n, then your j would, like, you'd never really have to care too much about like latency, because you can always just output everything. That makes sense. And then one thing that you want to do here is your ready in is just going to be your valid out. I forget if in the problem they have an input on the out for the valid. When I say underscore out, I mean the right-hand side of the mux, like the things that's going out, and then the left-hand side being in. So if they did, then it's actually, so I'm not ready when it's not valid out, but actually I'm not ready if, because if they're back pressuring and I'm valid, then it doesn't make a difference. The handshake's not acknowledged, right? So my ready in for any input I, well, actually this is not the case, because n and m are different dimensions. So anytime I pack I, then I would just say does this make sense? Because if I'm packing I to j, then my valid out for j is true. And then if my ready out for j is also true, that means that that handshake is acknowledged for output, let's say j here. But j could map to this or whatever, right? But you know what that mapping is, because we're always mapping from I to j. So if on j there's a handshake, then that means I can not back pressure input index I. So that takes care of this back pressuring situation, and then we also have this, and then we also need to be able to give start and end packet out. Actually, I don't remember if these are n wide or not. according to this, then each of these, like, it's kind of unnecessary for n. Like, you could just have one, because then I guess you could also say like 0 and then 1, but then that kind of violates stuff. Yeah, let's just say it's all the same, meaning like if I'm incrementing it, then obviously this is the end of the packet. And I guess if the outputs have the same restrictions as the inputs, which would make sense, then for example, if let's say for this, you have like 0, 0, 0, 1, like all the lines are valid, let's say, right? And you have, let's say, 3 outputs, then I guess your outputs could be like 2 of them for 0 and then 1 of them for 1. But then you would also need to keep track of your output states, because then if this is 1, it can't ever service 0 again. Like these 2 must be the only lines for 0. Okay, so for simplicity's case, I'll just do this, because I mean, yeah, as you can see, this problem is like quite involved. Like you could actually optimize this and say, if you could make it more advanced and say, if there's less than if there's less than n of my current state in an input, so let's say n was 3 and then there's less than 3 of like 0, which is my current state, then I want to allocate the difference. So like the rest of, like n is the number of going out, right? So if there's less, then whatever remaining, I could just go to the next one and then service that one. And then you could maybe go a little bit faster that way. Yeah. But I don't think I could do all of that in like 35 minutes. So if you want, you can do the more complicated stuff and let me know in the comments. But for now, we'll just say if we increment the output packet number, then obviously that signals the end of the packet out. And then since we're basically not doing this way, so I could see why in this way the start packet matters, because here you would say, oh, I'm starting for 1. And then here it's, but here I'm kind of just universally saying, I only care about zeros. After I'm done with all of it, I only care about ones. After I'm done with all of it, I only care about twos, and so on and so forth. But if you're doing it like that, then it's like very universal, right, on your entire output broadcast. It's almost acting as like a time filter. And this says, hey, end a packet out, boom, boom. And it says like, what is it? Like, yeah, end a packet out is when you actually increase. And then start a packet out can just be any time on the same cycle or before. Probably before, like at reset, can be start a packet out, and then you deassert it. until the next cycle. So you know, like this is kind of silly if you don't do the additional optimization. So start a packet out is actually all ones at reset, and then right out of reset, your startup packet out will just be dictated by this. So if you have an end a packet out, because of these sort of valid rules, like or this kind of redundant valid thing, and you're guaranteed that your data is like there's no valid packets of data that will come in. And also, you know, because of this packing filter here, we're guaranteed that we're not going to output any data that's not actually valid. So, because of this check, right? Like we need this, because this in.valid passes through to data out.valid. So we're not going to leak any data there. So anytime like we end a packet out, let's say for 0, the next cycle we say, okay, well, this is start of 1 now. Yeah. And then because this will only increment, generally it's not back to back. If it's back to back, then it's like one sequence per cycle. But if m is bigger than n, you're not going to do it every cycle. It's not physically possible. But let's say you do end a packet out, and then next cycle, you start a new epoch, and then, but then like right then and there, you actually exhaust everything somehow, like m equals n. Then your end a packet out would be asserted again. Then it's okay that the next cycle, that the start of the packet out, because then you just you're transforming the output states from 1 to 2. And I believe that should wrap it up if I have no syntax errors. I probably won't bother testing this out because then there's so much, yeah. But you can see how this is involved, and then you can also see how like if instead of scanning all the zeros, you output zeros, and then scanning all the ones and you output all the ones after all the zeros are done, you could also say, like actually only like if less than n matches, like less than n cases where this, right, less than n cases where your packet is going to be the same as the input, then you could say, well, then what is that number? Then you take like n minus whatever that less than n is, count of matches, and then num2 increase, right? And then you can do like for like you could do like output state, which I don't have because my output state is just a singular state, but you could also have like n-1 states. But you could have like, if you did it the other way, instead of like this, then you could have like output packet, I'll just call this output packet numbers instead of number. Then you could do like like n. So if you're packing from the LSB to MSB, then that means n-1 to the n-num2 increment. So for example, if you have 3, then it's n-1 to n-3 inclusive. So for example, 5 is your n, then it'll be like 4, and then like num2 increases like 3, then it'll be 5 minus 1, and then 5 minus 3, which is 2, which would be 3, plus plus, for example. Then in that case, your remaining ones will like increase. Now this gets a bit nasty because you can only do this once. Because for example, then like let's say these goes to 2, 2, then then how many times can you do this, right? Like, and then until your steady state is like your input stream has n unique packets as inputs, and then each one of these would just service each one of them, which is a bit slow. There's probably some optimal math solution, but yeah, I mean, like within 35 minutes, how are you going to do that, especially if they're interrupting you every few seconds? And then the other question that they asked, which is a Python question, was basically like implement the decorator cache. In case you don't know what that is, a cache is just saying basically memorize the answer when you call a specific function with specific input args. So for example, you can, like, for example, you have factorial, which then calls recursively all of n-1 factorial, and this factorial of 10 will memorize all 11 recursive calls, so 10 to 0, and then so all, like the first time around you need to actually calculate it, but then since in memory there's factorial 0 all the way to 10, the next time you call like 5, it can just pick up that mapping. So for example, like if you have like a cache dict, then you could just say the cache dict of the function, or like the func pointer, the pointer to the function, and input args maps to the result, right? If you think of it that way, so in this case, like, then factorial 5 would already be stored because the first call of this has, factorial, and then all the way from 0 to 10. And then factorial 5 hits because 0 to 10 includes factorial and 5. And star args is just basically a variable input. So this could have any number of inputs. And then so you have this, and that would memorize. And then if you do this, the other 10 are cached. Then you need to, this is smart enough to start from, I guess, 10, if it's a recursive call. So I guess in your algorithm, if you see like a bigger number, and then you run through it, then you need to make sure that, actually, yeah, if you call 12 and then it'll call 11, and then 11 will call 10, 10 will hit, this basically cache dictionary, and they'll just return the result. Yeah. So it's just to implement that, but then during the course of like this implementation, they're like, no, you want to return a function handle. So I'm like, all right, cool, and then I implemented that, and they're like, oh, no, you need to return a result. So yeah, I mean, that was kind of a waste of my time, but then this problem is actually pretty interesting if you want people to never work with you again. That's a great question to ask.